So let's now go ahead and talk about part 2 of our discussion of navigating our AI-augmented future. And here we're going to talk about the impact of AI augmentation in the software development process, how people build systems using these tools. So it's going to be this piece of the quadrant right down here in the right-hand lower corner. I'm going to start out with a very high percentage prediction. Anybody here, you're probably way too young to remember Dr. J. He was a basketball player in the mid-70s who played for the Philadelphia 76ers, and he was very famous for dunks. So he came up with all kinds of cool dunks way before Michael Jordan and LeBron James and so on. So they called him Dr. J. And someone once asked him, why do you like to dunk, Dr. J? And he said, well, it's a very high percentage shot, because as long as you can soar above the ground and throw the ball into the hoop, you're probably going to get the 2 points. So my very high percentage shot is generative AI is and will continue to have a transformative impact on the practice of software development and quality assurance, how we build these systems. And in fact, this is one of the topics from our national agenda that we did. And you can read some cool articles about people's predictions of how this is going to affect the future of software development and software engineering. How do I know this? Why do I feel this? Well, it turns out over the past year, and this is increasing in frequency, AI-based tools, AI-augmented tools, are increasingly available to improve the way we build software and the quality of our software because they help to reduce cognitive load. For those of you who are just starting out doing programming using tools like ChatGPT and other tools, you're probably not as familiar with the concept of cognitive load of writing software. If you go through a more traditional path through our computer science curriculum, you'll spend a lot of time learning languages like Java and JavaScript and Python and C++ and so on and so forth. And you'll discover very quickly there's a lot of really tedious and mundane and often error-prone things you've got to do when you build software. And the nice thing is a lot of those tedious and error-prone steps can be offloaded from you by using the right set of tools. And a lot of these tools these days are what we call AI code assistants or chat buddies. So things like GitHub Copilot, Amazon Code Whisperer, Tab9, Android Studio Bot, the list goes on and on and on. There's a whole bunch of them listed here and reviewed. So this is something I use when I write code now. One of the great things I love to do with this is write comments, which are important, but sometimes are things people tend to skimp on. But generative AI tools do a really nice job of documenting what you're doing because they are more patient than we are often, and often have a better global view of what's going on in the software. I've been applying these technologies in my courses. If you take my courses at some point, you'll get a chance to do this too. You can take a look at this video for examples of how we're using this in the courses I teach here at Vanderbilt for all kinds of cool purposes. We're probably not going to get to this topic today, but when I come back for a future lecture, I'll have a second part of this talk where I go through how we use this stuff, and you'll get a better chance to understand what it can be used for in practice. What's interesting, however, is not everybody is equally bullish or excited about applying these tools to people doing programming or doing the stuff that you're doing in this course, which is a variant of programming. There's an article by a very famous computer scientist named Bertrand Meyer that appeared about 7 months ago, which has the very provocative title, AI Does Not Help Programmers. Now, here's just an unsolicited tip. Whenever you think about how people are going to remember you in the future, be very careful not to make claims that quickly will be overtaken and make you look like you didn't know what you were talking about. Here's a couple of good examples. In 1943, Thomas Watson, CEO of IBM, said, "I think there will only ever be a need for 5 computers in the world." Didn't age well, did it? In the 1980s, Bill Gates, one of the richest men in the world, was the richest man in the world for a long time, till he started giving his fortune away. He famously said, "Who would need more than 640 kbytes of memory?" Didn't age well, did it? Bertrand Meyer, AI does not help programmers. Not true. Didn't age well. And it's really curious why people find themselves compelled to say these kinds of things. There's a couple of ways I explain it. One way is people have unrealistic expectations about what these tools should have done in the first few months of coming out. And unfortunately, to some extent, we're saddled by people who took a couple shots at using this stuff back in 2023, January, February timeframe, where things were still pretty loosey-goosey and flaky, concluded they didn't solve all the problems, and then decided they don't work at all. It's a waste of time. This is never going to get any better. It's a fool's errand to think this is going to be good. That's kind of like a sculptor, like, say, Michelangelo, seeing a block of marble, taking a chisel, whacking it a couple of times, and then not having it turn into the Pieta instantly, and concluding, see, sculpting is a waste of time. I'm not a sculptor. Nobody should devote their life to sculpting. You have to be a little bit more dedicated in order to be able to create masterpieces. The other thing that's very important here is a lot of people who say these things don't actually spend a lot of time writing programs day to day. And if you spend time writing programs day to day and you use these tools, and you learn prompt engineering, which we'll talk about, you can do amazingly wonderful things. In fact, because this is a very common phenomena, hopefully it's getting a little bit less of a phenomena because people are starting to really realize how effective these tools can be. I actually coined a term which I call degenerative AI. So we know what generative AI is. It's about creating things out of training sets that have been learned that are creative and interesting and novel and perhaps new. Degenerative AI occurs when pundits dismiss the power of generative AI based on only a handful of use cases that don't properly leverage generative AI tools in the right way. They don't use the right tools. They use early tools, not later tools, and/or they don't properly understand prompt engineering and prompt patterns. So I actually asked ChatGPT to generate this image using DALL-E, and I said, generate me an image of degenerative AI. And this is what it generated. It has this tree of artificial intelligence or augmented intelligence and people who are shackled to the old way of doing things surrounding it. So I thought that was a pretty cool way of getting ChatGPT to visualize this phenomenon. There's something else that's important to think about. Now, some of you might end up wanting to go on and do computer science stuff at some point. Most of you most likely will use these technologies to do computationally enriched things in research or your professional lives or education or whatever you might end up doing after Vanderbilt. And a lot of people are very worried that these tools are going to devalue the role and importance of software development and expertise with software engineering. It's a legitimate concern. However, there's a couple of things to think about. First of all, the history of software engineering for the past 60 or 70 years has always been one where a set of technologies, languages, platforms, methods have been systematically augmented and replaced by newer things that built on top of them. And therefore, the skill set that you used to have to know to be effective at some level, let's call it level 1, no longer is necessary to know as you get to level 2, 3, 4, 5, 6 up the stack. A great example of this would be assembly language programming. Back in 1950s, if you wanted to be a programmer, you would write assembly code, and you had to master the fine art of hand-allocated and optimized register allocation. Oh boy, what a complicated thing. Today, just about nobody has to know the least bit about hand-optimized register allocation. Why is that? Because compilers came along that were much better at it than we were. Likewise, early 60s, Fortran came out. A lot of people who were programmers in assembly code said, oh my gosh, this is it. We're going to be out of a job because all the managers are going to write the code. We don't need programmers anymore. That didn't age well, now did it? In fact, when you take a look, every time there's been a new advance in technology, instead of reducing the need for people, we've actually accelerated the need for people because of the Jevons paradox. So if you take a look at this link here, or you just Google the Jevons paradox, it basically is a predictive model that says increased efficiency in technology, in this case software engineering, will actually yield greater need for developers due to the expanded growth in market demand and the complexity of the systems we're building. So we're not going to need less of this stuff. We're going to need more of this stuff because there's going to be more demand. And if you think back, maybe even back when you were starting out with computing, say 15, 20 years ago, when you were 6 months old and you were using touchscreen devices, things have changed radically since then. And yet we have more and more demand for this stuff, not less. However, the things that we need to do as developers or power users, if you're someone who's using ChatGPT, you have to become experts in new areas. You can't continue to be an expert in hand-generated and optimized assembly code register allocation. That's not going to cut it anymore. No one's going to need that because it's going to be replaced by tools. So being able to do prompt engineering effectively will become a very important skill. Knowing how to test and train large language models for some of you might become important. I don't think there'll be a huge number of people who have to do that, but you'll certainly have to know how to use the LLMs effectively to get them to do your bidding. Learning to deal with non-deterministic outcomes. Big issue, because when you work with these tools, you don't always get the same result when you ask the same question. That's usually by design. That's often good if you're trying to approximate the way people interact, but it's not always what you want if you're trying to build a system that has to last a long time and be survivable and efficient and suitable for purpose. So I asked ChatGPT to generate me something where we have a world of the future and it has these robots doing a bunch of stuff and sort of cobwebs and things. I'm not really quite sure what this means, but it looked cool. So let's talk about some of the challenges and opportunities in this space. And I'm going to focus kind of on things that are coming down the pike, although a lot of this stuff is coming faster than you might think. There's also another link here that has a whole video that goes into this in more detail. So one thing that's going to happen, it's already happening, is people are beginning to train the language models on better vetted, robust, and perhaps specialized code bases. Why is this important? Because the very first generation of stuff that came out a year or so ago, back back in the Stone Age, if you will, were not necessarily trained on the best input. So they were trained on Stack Overflow postings, the contents of GitHub repositories, which admittedly probably had a lot of bugs and defects in them because people write a lot of bugs and defects. So it might come as no surprise that some of the stuff that came at that point wasn't as good as we might want. So what's happening now is people are starting to spend a lot more time training models on good code. So things like the CodeGen project from Hugging Face. There's also the GitHub Copilot that Microsoft is involved with. They're actually training on very good bodies of code. Therefore, the output should hopefully be better. And what they do, if you're not familiar, you probably already know this from other lectures you've heard from people like Jesse. This is what's called an autoregressive model, which sounds like some kind of Freudian psychology psychosis. Autoregressive sounds like a problem, but that's actually the way that they train these systems. And again, you probably know this, but very quickly, the way these systems are trained is they take a very large amount of data and they go through the data and they remove words or phrases or tokens, and then they try to train the system to predict what comes next with a certain amount of probability. So here's a very simple example you can read more about at this link, where they're trying to get the system to know that the Trevi Fountain, which is in Rome, is in the center of Buenos Aires, probably low probability. Rome, high probability. And that's the way these models have historically been trained. Now, if it sounds kind of brute force, it is kind of brute force. That's why it takes a lot to train these models. It's also funny because a lot of the degenerative AI pundits will dismiss this by saying, isn't ChatGPT just an auto-completion mechanism? Just like spell anticipation when you're typing words in a web browser? And if you take a very reductionistic sort of silly view, then yeah, maybe. But when you start actually seeing how this stuff works in practice, you realize it's a heck of a lot more than an auto-completion mechanism, especially when you start to use newer tools and newer techniques and newer patterns, such as in-context learning and chain-of-thought reasoning, which allow you to do very powerful things on data that the large language models were in fact not trained on to begin with, which is really cool. Now, not surprisingly, because of the way they train things, the strongest language support is for the most common languages. So you're going to see things like Python, JavaScript, Ruby, if you're a Google person, Go, which is a Google-centric programming language. And these are the languages that get the best support. However, some communities don't use those languages. So for example, if you work in real-time embedded systems, if you work in military aerospace systems, then those languages and tools are often different. Moreover, the quality attributes, the need for dependability and predictability and survivability and the responsiveness, these types of issues, they are quite different from what you get with your garden variety e-commerce system that is so popular and being used today. So all these mission critical systems, safety critical systems have much different requirements. And in fact, people often write down policies for building these systems and put them into various documents that you can download and play with. And we'll come back to that in a second. One in particular is called the AFMAN for Air Force Manual 91119, which describes policies and guidelines for the safe design and evaluation of nuclear weapons. Probably something you want to work correctly. You don't want it to go boom at the wrong time. Another interesting dimension here is a lot of these embedded systems, these legacy systems, are developed and sustained using non-mainstream programming languages, things that very few people know anymore. So a good example would be COBOL. Very few people actually learn COBOL these days. Jovial, which sounds like a very pleasant, friendly language, but it's a very old language. Ada, been around for a long time, developed in the early 80s. Very few people know how to program with these things. So it wouldn't come as a surprise that for people who have to maintain and sustain these systems in all these somewhat obsolete languages would find specially trained large language models very useful for them to be effective. Another dimension where R&D is required and is happening is in re-envisioning the way that the software development lifecycle can leverage these tools. And again, just for completeness, the software development lifecycle is all about figuring out what you're going to do. That's the planning phase where you determine your requirements, analyzing the trade space to understand what the different ways of building the system are and what the pros and cons are, designing and architecting the system to think about the major components and how they connect and interact. Then, of course, the fun part, which we computer scientists spend a lot of time doing, the implementation or programming phase. Then there's testing and integration where you make sure everything works. And of course, then over time, if you're successful, you have to maintain the system. And this doesn't really look, this looks sort of like a waterfall model, but these things occur in very short cycles now and phases using methods like Agile. Most research on large language models to this point, and most attempts to apply them to software development, has focused on the downstream phases. So the generation of code or the generation of test cases. And if you take a look, you'll see a whole bunch of papers that talk about this. And this is great stuff. However, there's other things that we need to do, and there's actually other parts of the software lifecycle that can benefit from applying large language models. So here's a very simple example. There's a problem that people run into when they use more modern techniques like Agile, where you're trying to do things quickly, fail fast, learn fast, tight cycle times, that kind of stuff. You can often accrue what's called technical debt, which are things you didn't deal with at a given point, and you push them off to the right to deal with later. And those things can become a huge encumbrance on being able to build these systems over time, because the technical debt will crush you. So people have done some really cool stuff by using machine learning to take a look at various repositories to try to identify areas of technical debt so you can more proactively pay down that debt. More generally, there are non-code artifacts that can be analyzed at scale using generative AI better, faster, and cheaper than humans can do it alone. And this is where we really see generative AI shining in the software development lifecycle. So here are a couple examples. Requirement, meeting notes, risk assessments, project vision statements. These are all data that occur very early in the lifecycle of most systems. Of course, they get refined over time. Developing the product, there's documents that document the system architecture, the software architecture. There's diagrams that visualize the source code and its relationships, or the entity relationship diagrams and so on. There's testing and quality assurance. There's test plans, benchmarks, all these kinds of things that you have to put up so you can know that your system's actually doing the right thing. Deployment, phase, artifacts, container images, DevOps pipelines, continuous maintenance and improvement of the product, user stories, roadmaps, end user agreements. These are all things that humans today have to plow through manually, and it's very complicated, but generative AI can make a big difference. So in my perspective, the big benefit from using generative AI for these upstream phases in the software lifecycle is the criteria for success is as good or better than people do it versus perfection. If you wanted to use a compiler and the compiler was going to generate really efficient code, but only 95% of the time would the code be correct, you probably wouldn't want to use that compiler. So the criteria for code and testing is perfection. That's the baseline. We want things to be perfect. But for a lot of these other tasks, people do a really poor job at scale. So you just need something better than what people can do. It's kind of like the old joke about someone who's a hiker who's being chased by a bear. And the question is, you don't have to outrun the bear. You have to outrun your friend who's being chased by the bear too. So you just have to be better than the other people and their ability to do things. So here's a very nice example that makes this point. So once again, this is the AFMAN, Air Force Manual 91-119 for evaluating nuclear weapons software. And when people read this document today, it becomes almost like theology. People don't really read it for what it says. They read it for what they think it says. However, tools like ChatGPT can take a cold, objective, steely look at the document and find inconsistencies, find gaps, find inconsistencies both within the document as well as comparing to other documents. And that gives you new and different insights that you wouldn't easily get when people do the work. And so we've actually done some work on that we'll be publishing here soon that has applied large language models to analyze these documents. In fact, this concept is given a name. It's called discrepancy analysis. And you can probably imagine that discrepancy analysis would turn out to be useful for all kinds of other fields besides software engineering. So if you're a lawyer, if you're a doctor, if you're someone who does auditing as an accountant, being able to look for discrepancies between documents, incredibly valuable. So that's a big area that we're going to see going forward as a good use case for this stuff. Some other things that are important is to be able to increase the use of AI tool support throughout the software lifecycle. So trying to get more stakeholders involved. Programmers are a big part of what software is about, but there's a lot of other people in the value chain. And one of the things that we're seeing here that's becoming very promising to eliminate or alleviate or minimize the hallucinations that the first generation of these LLMs were characterized by is something called retrieval augmented generation. And basically the idea is you take documents and you chunk them up into smaller pieces, and then you take those chunks and you vectorize them, you encode them, and then you put those encodings into a database. And then when somebody asks a question to an LLM, rather than going out and trying to do this auto-completion, statistical replacement of text type approach, which people like to mock, instead it goes and it looks up in the vector database and tries to find the entry point into the description to answer the question. I like to think of this, if you're familiar with Harry Potter, concept of the pensieve, which takes a strand of your thought and you put it into the little pool that Dumbledore has in his office. And then you can take that strand of thought and then reimagine and understand what that person went through. Basically the same idea, just a little bit more real than magic. And so when someone asks a question with an LLM that is using retrieval augmented generation, it goes and looks up and tries to find the parts that give the answer, and assuming it can find it, then it does all the fun chatbot stuff to make it conversational and interactive. But if it can't find it, rather than just randomly hallucinating with some statistically probabilistic response, it says, I don't know. You almost never get an answer back from the RAG-enabled LLMs that say, I don't have the faintest idea. Instead, you just get back a random answer that is hallucinogenic. So this is becoming very popular, and I think it's going to go a long way when combined with things like prompt engineering, when combined with other things like augmented intelligence, people in the loop, to making these systems a lot more predictable. We're doing some work on this at the Software Engineering Institute, where we're actually taking these compliance documents for writing secure code and safety critical code and extracting from them policies and guidelines and rules. And then we use those policies, guidelines, and rules in order to be able to check source code to see whether it complies with or diverges from these policies, guidelines, and rules. And this is another form of discrepancy analysis that allows a broader range of people to be part of the process rather than the historical way of doing things where only people who knew how to program in very esoteric query languages for static analysis could play. You can get a broader range of stakeholders involved in trying to identify whether the systems behave properly. Another theme that's coming out here, I'll just touch on very briefly in the interest of time, is integrating the generative AI approaches into the DevSecOps pipeline. That may or may not mean much to you if you're not into modern software development, but the idea here is that we want to be able to have our systems that we're deploying be in a state of almost completion and almost certifiable, releasable, authorized to access and authorized to act kind of form at all given time. And to do that, we build tool pipelines that will continuously check the software as people make changes to it to make sure all the test cases work. And there's lots of cool things that you can do with generative AI in order to augment and enhance the DevSecOps pipeline. You can take a look at some examples at the link here. Another thing I'll say before we change topics, one of the big problems when you work in large organizations, especially things like government projects, especially military projects, or large-scale infrastructure projects like building electrical power plants or the SCADA systems, which are the control systems that are used to acquire data and do things like manage the power grid and so on. You often end up with tons and tons of PDF files, Word documents, PowerPoints that are very document-centric and very difficult for people to keep track of at scale. So you get crushed once again with the weight of all the complexity and all the different things that nobody can keep track of in their little human monkey brains that we all have. So a better way to do this is to use these generative AI tools in order to enable dynamic, information-centric processes to develop, validate, and sustain these software-intensive systems or software-reliant systems. And there's a nice video here that you might want to watch where they're talking about some work going on in the operational test and evaluation community to try to improve the digital infrastructure for keeping track of all this stuff, which is so important if you want to deal with very large-scale systems. So let's kind of switch gears now and talk about something else that's super important in the space of using generative AI effectively. Hopefully you're getting a chance to be exposed to this in this course, but if not, here's a teaser for it. You'll probably get to it soon. Prompt engineering. So what is prompt engineering? Prompt engineering is basically a way of having structured interactions with large language models, ChatGPT and the like, to solve complex problems using natural language as the programming interface. The point of this is to focus on problem solving rather than traditional computer programming. Now, I love to program, but really programming is a means to an end. You're trying to solve a problem. And if we can solve that problem without having to write code in JavaScript or Python or C++ or whatever third or fourth generation programming language you might want to use, so much the better. And here's a nice little visualization. I asked ChatGPT to generate the difference between programming and problem solving using prompt engineering. And I thought that was a pretty nice way to visualize it. This is very useful for programmers because we can use prompt engineering and LLMs to improve how we write our code. For example, we can do things like refactor the code to take advantage of new languages, new libraries, new features, and so on. We can also refactor the code or transform the code to make it more optimized. So these are things that are good for us as software developers. However, I think an even more useful way of looking at this is for people who are not programmers, people who want to use computation to solve their problems, but are not actually going to program or don't want to learn to program in Python, JavaScript, Java, C++, or whatever. In fact, back in the day when my colleagues from physics or biology or classical civilization or whatever from other parts of the school would come and say, I want to use computation in my work, my research, my classes, our inclination for many years was to say, great, I'm going to teach you how to program in Python. I'm going to teach you how to program in Java or JavaScript. The problem was that's the wrong level of abstraction. People wanted to use computation. They didn't want to learn to be a programmer. So for people like that, people who are going to be scientists or operators, smart people but not programmers, these tools can be tremendously useful to unlock their creative insights in ways that would be hard to do otherwise. I don't have enough time to go into that today, but when we come back, I'll give you a much better example of this. Something else that's really valuable is codifying the way of doing prompt engineering in the form of pattern. Now, again, this is probably maybe more software engineering than you need to have for this course, but people who are good at programming for the past 30-some years have been thinking about codifying their programming knowledge and their design insights in the form of pattern. And I've written a whole slew of books on this. I've got friends and colleagues who've written a whole slew of books. And basically, a pattern is a reusable solution to a problem that arises when you do something in the context of software, some domain, like user interfaces or databases or real-time systems or electronic transfer systems or whatever. So the concept of pattern has been around a long time. And it turns out that there's also patterns for interacting with large language models. In fact, here's a paper that we wrote about 6 months ago that's wildly popular. It's got hundreds of citations so far. And it tries to codify best practices for phrasing prompts in order to maximize the chance the LLM will give you a sensible result and to be able to do knowledge transfer to problem solve more effectively. So once again, we think about this as sort of programming. And so we've been defining prompt catalogs for different phases of the software lifecycle. This is another paper that's also got a lot of citations that talks about this. I think this is going to be really important in the future. Now, some people are of the opinion that prompt patterns are sort of this dysfunctional, retrograde way of making up for the fact that our large language models aren't yet ready for prime time to have ESP and intuit exactly what you're trying to ask, and they hope that we'll get to the point sort of like the Star Trek Next Generation computer where you just talk to it and it knows exactly what you want. I think that view is wrong for a couple reasons. First, because natural language is the means by which we interact with LLMs, natural language is inherently imprecise by design. Sometimes it's actually a good thing. You can be imprecise in ways that actually help people communicate more effectively. However, that means that we are always going to have to find ways to communicate with the computers to get them to do exactly what we want. And you don't have to go very far to see how important it is to phrase things correctly to an LLM. In general, the more context you give it in the prompts you ask, the more accurate and sensible and useful the results you get back from it will be. Moreover, and here's the real thing, people who think that prompt engineering is just a bunch of parlor tricks to get your LLM at the moment to do your bidding are missing the bigger point of prompt engineering. And just like software engineering is not just about writing code in your favorite third-generation language, it's about the life cycle issues. So too is prompt engineering needed to be looked at holistically. So testing of the ways in which you interact to make sure you're getting results back that are accurate and precise and not hallucinations. Doing version-to-version management of changes when the LLM changes, making sure you still get useful output. Big deal. Configuration control. All the kinds of things we sweat over when we build large-scale software systems with large groups of people, prompt engineering needs to be also oriented to that. And I want to make that point particularly in this type of a class, because this type of a class is really not expecting you to be a software engineer. You're not focusing on all these other long-term life cycle sustainment issues. You're focusing on ways of using these tools to do an assignment or two that are better, maybe more interesting than if you tried to do it yourself with just your brain. However, that's not the real world. And in the real world, we make a big mess and we accrue piles of technical debt when people don't think holistically about the life cycle of this stuff. Okay, so that's the end of part 2.